So let me start by saying that, yeah, a little bit over a year ago, it was still in the early days of lockdown, my co-organizers, Jean-Philippe and Jay, they came up with this idea to organize a weekly online seminar to bring this community of people in computer-assisted mathematical proofs in nonlinear analysis together. And when I look back on this past year, which was pretty monotone, being at home in front of my laptop, these weekly meetings have really been a highlight of my week. So thank you, Jean-Philippe and Jay, for taking the lead in this. Now today, celebrating basically the 1-year anniversary of the CRM Camp Seminar, it is my absolute pleasure to introduce our speaker, Professor Charles Fefferman from Princeton. He received his undergraduate education in both mathematics and physics at the University of Maryland, and then his PhD at Princeton under the guidance of Elias Stein. And then he became a professor at the University of Chicago right away. And then 4 years later, he moved back to Princeton, where he has been ever since. He was the first recipient of the Waterman Award in 1976, and then, as probably we all know, was awarded the Fields Medal in 1978. And I could go on and on and on and on, listing his numerous awards and achievements, but I think we all know how influential his contributions have been to fields such as mathematical physics and nonlinear analysis, but also recently in finding manifolds in data. Today, the topic of his talk will be going back in history to the 1980s, to the early days of computer-assisted proofs. Please, Professor Fefferman, the floor is yours.
Hi. So thanks for the kind introduction. I hope that that we will all enjoy this this hour. Am I right? This should take about an hour.
Yes.
Okay. So first of all, I know I am speaking to a community of experts who produce computer-assisted proofs. I should say right away, I am an occasional consumer of computer-assisted proofs. All right. Let me switch to my document camera, which will start to make the point. There we go. So I'm going to reminisce about my very first encounter with computer-assisted proofs. I want right away to thank the people who have unlocked for me the power of computer-assisted proofs. They are Rafael de la Llave, Luis Angel Seco, and Javi Gomez Serrano. Actually, Javi, who is here today, collaborated as part of a team to which I belonged also, doing things that in the end were not computer assisted, but nevertheless, he is of course an expert in this subject, and these are the three people whom I have relied on for when the computer has to play a role in a proof. Okay, in particular, Rafa and I wrote a paper long ago on something called relativistic stability of matter, which will be the subject of this talk. Luis Seco and I collaborated on a series of paper on the ground state energy of a single atom of atomic number large compared to 1. And Javi and several other people and I worked together to prove that singularities form in water waves. I think I should move my pad of paper there. By the way, I hope to snow nobody, so please feel free to interrupt. I am techno challenged, so if you want to get my attention, don't put anything in the chat, just unmute yourself and speak. Okay. So my plan is to describe my very first encounter with computer-assisted proofs that happened in the 1980s. Back in the day when, for example, the president of the United States was Ronald Reagan and the USSR existed and was led by Gorbachev. All right, so the subject is relativistic stability of matter. Okay, so I'm going to start with ordinary stability of matter. I'm not going to assume that you know anything about quantum mechanics or that maybe, well, I'm going to, right. So please don't feel insulted. I would rather bore you than snow you. So, all right, we have in three-dimensional space, we have fixed nuclei at positions y1 through ym, and we have quantized electrons and we denote their positions by x1 to xn. So think of, for example, a box of hydrogen. M and N might have the order of magnitude of, I don't know, 10 to the 30th or something like that. Now, these particles interact by Coulomb interactions, and they are governed by the very simplest version of quantum mechanics, about which I will say a little bit. So in the very simplest version of quantum mechanics, the protons are just sitting in fixed positions because we don't bother to quantize them. But the state of the system is a wave function, psi, of the electron positions, and that psi is a vector in L2, and its L2 norm is 1, so that the total probability of everything is 1. And a very important property of electrons is that they are fermions. So if you interchange two of them, that flips the sign of the wave function. And so there, as you see on the slide, if you permute the x's, that has the effect of multiplying the wave function by the sign of the permutation. Here, I'm neglecting the spin of the electron. Really, psi is not scalar valued. Never mind. Let's take this as the simple version of quantum mechanics. Okay. Now, a basic self-adjoint operator that plays a tremendous role in quantum mechanics is the Hamiltonian, which is written on the slide. So we have the sum over all the electrons, J, of minus Laplacian xj, that's the kinetic energy of the jth electron, plus a multiplication operator. And what we multiply by is V Coulomb, the Coulomb potential, written on the slide. Notice the electrons repel one another, the nuclei repel one another, and there's an attraction, the minus sign, between each electron and each proton. And so this is the Coulomb potential, and this operator acts on antisymmetric wave functions. Okay, and it's important that it act on antisymmetric wave functions rather than all wave functions. Okay. Oh dear, here. One of the here that this method of using paper and pen and a document camera is almost idiot proof, but I have trouble separating the pages. Okay, the energy of the system in quantum mechanics is the inner product of h psi with psi. H is the Hamiltonian, and stability of matter is an inequality for the energy of the system, which says that the energy of the system is bounded below by, let's say, some negative constant times the number of electrons. So this C is a universal constant, an important universal constant. It's a priori not obvious that this is true if for no other reason than that the number of interactions goes as the square of the number of particles. Every particle interacts with every other particle, and yet the energy is bounded below by something which is linear in the number of particles. Okay, so this is called stability of matter. The physical meaning of stability of matter is that collections of many electrons and nuclei do not collapse into a superdense state. And the constant C in the estimate that I just showed you in stability of matter has physical significance, but we're not going to get into that because I've got a lot of slides and not much time. Okay, this estimate stability of matter was proven first by Dyson-Lennard with an enormous constant C, and again by Federbush with a different proof, but also an enormous constant. And then I think in the early 70s by Lieb and Thiering with a not so enormous constant, with a reasonable constant, although the best constant is still not known and is an interesting problem. Okay. Now, the work with Rafa that I'm going to talk about is about a variant of stability of matter called relativistic stability of matter. And so I'd like to prepare the way with a smidgen of physics. And after the smidgen of physics, I will state the theorem on relativistic stability of matter. And then most of the lecture is going to be about the proof. and maybe the relevance of this ancient theorem to today's talk is that eventually we're going to reduce matters to simpler and simpler things, and finally it's going to be reduced to a statement about ODEs, which is checked by a computer-assisted proof. And so this was how I came to be introduced to computer-assisted proofs. Okay, so let's start with the smidgen of physics. So in high school physics, one learns that the kinetic energy of a moving particle is 1/2 mv squared, and that the momentum P is mv. And therefore, since the high school student has learned elementary algebra, the kinetic energy can be written as 1/2m times P squared. Okay, let's pick units in which 2m is equal to 1, and so the kinetic energy is simply P squared. Okay, well, all right. So after taking high school physics, maybe one takes a course in university physics and learns a little bit of quantum mechanics, and one learns that the momentum P is actually an operator. It's plus or minus I times the gradient. I'm afraid that I took elementary quantum mechanics more than, oh my God, roughly 60 years ago, so I don't remember the sign. Fortunately, it doesn't matter because the kinetic energy is P squared, which is then minus Laplacian. And that's why this expression, whoops, there's supposed to be an x sub j. That's why this expression appears in the Hamiltonian in the statement of stability of matter, because it expresses the kinetic energy. Okay, fine. Well, however, a bit more elementary university physics, special relativity. In special relativity, the kinetic energy is no longer 1/2 mv squared, or no longer P squared over 2m. Instead, it is this thing. When P is small, that's the non-relativistic regime, you can Taylor expand and you get back your familiar 1/2 mv squared. But if P is large, that's grossly inaccurate. For large P, this thing is asymptotic to the absolute value of P and not the absolute value of P squared. So the kinetic energy is much smaller than one might think. Oops. Okay. So that motivates the idea of changing minus Laplacian to the square root of minus Laplacian. Let's say defined in terms of the Fourier transform. The Laplacian multiplies by the square of the frequency, and the square root of the Laplacian simply multiplies by the absolute value of the frequency. So that would suggest that we consider instead of the elementary quantum mechanics Hamiltonian that everyone is familiar with, this guy, where we put a square root here. Notice there's no constant here, there is a constant here. Here, any constants have a dimension which can be scaled away, and here these things are of the same dimension. The constant is dimensionless and cannot be scaled away, so it's there. So this guy is the Hamiltonian that we're going to study.
Can I ask a question?
Sure.
This summation, it is not inside the root, I see it is.
That's correct. That's correct, okay. Because each electron has its own kinetic energy.
Ah, okay, sure. Thanks.
Okay, well, thank you for asking the question. This proves experimentally that one can ask a question and get an answer. Okay. Okay. So the square root is definitely not on the sum. It's the sum of the square roots. Okay, so that's the Hamiltonian we're going to study. Now, physically, that's not correct relativistic quantum mechanics. In fact, correct relativistic quantum mechanics does not at this moment exist as a consistent mathematical theory, and may never exist, because maybe it's important to consider other physics than just electrodynamics at small scales. Oh, I just said, no, there will be a relativistic quantum mechanics, but it doesn't exist today. But nevertheless, this is a reasonable thing to consider. It predicts orders of magnitude of actual physical phenomena, most notably the collapse of neutron stars. So in, I think, the 30s, Chandrasekhar and maybe Fowler predicted sufficiently big stars will collapse into neutron stars based on exactly this reasoning of replacing the Laplacian by its square root. So that's the physical motivation. Mathematically, the point is that stability of matter, which is an interesting inequality, is not a sharp inequality. Rather, it's an elementary consequence of relativistic stability of matter. So let's see why that's true. So here's the relativistic Hamiltonian with a constant which I've called kappa. Now, all right, kappa can't be scaled away, it's dimensionless. But we will see in a minute that if kappa is big enough, this relativistic Hamiltonian is non-negative. If h isn't big enough, then actually this is unbounded below. We can make the energy arbitrarily large negative. We'll see that in a minute. Oh, in fact, yes, on the very next slide. So, okay, so let's look at just one electron and one nucleus. So we have a single square root of a Laplacian acting on functions on R3 rather than antisymmetric functions on R3n. Okay. We're subtracting the Coulomb attraction to a single nucleus fixed at the origin. There's our constant kappa. Now, this guy is dilation invariant, so it can be analyzed the Fourier transform in the log. Analyze this thing using the Mellin transform. You can just at least pi over 2 the Hamiltonian, whereas as soon as kappa is smaller than pi over 2, the Hamiltonian is unbounded below. Okay, so this constant had better be at least kappa over 2. This is only one electron and one nucleus, and who knows what will happen for many electrons and many nuclei. Okay. Relativistic stability of matter. So the theorem that Rafa and I proved, and that I'll talk about today, is that this variant of the usual Hamiltonian with the square roots acting on antisymmetric wave functions is indeed always greater than or equal to 0 for every antisymmetric wave function, provided that kappa is greater than or equal to 2.06 pi. So instead of pi over 2, we have 2.06 pi, but with that increase in kappa by roughly a factor of 4, we gain that instead of just looking at one electron and one nucleus, we look at arbitrarily many electrons and nuclei. Okay, so that's the theorem. And again, the punchline at the very end is that this is going to be proved using a computer-assisted proof. And so how do we get from this to computer-assisted stuff? Okay, now I said before that relativistic stability of matter implies ordinary stability of matter and with a not so bad constant. And the reason is that anything is greater than or equal to kappa times its own square root minus kappa squared over 4. Okay, and so if you plug that in with the kinetic energy, here is the Hamiltonian for ordinary stability of matter. Here is the Hamiltonian for relativistic stability of matter. We have this term. It used to be just kappa squared over 4, but now there are n electrons, so it comes with that factor n. And now this guy is greater than or equal to 0, and therefore this guy is bounded below by minus kappa squared over 4 n. And kappa squared over 4 for us has the order of magnitude is approximately 10. And so the constant in stability of matter is about 10. The correct constant can be measured in the laboratory, and it's a little bit more than 1/4. So 10 is not so bad. Okay. All right, so the rest of the talk is going to describe the proof of relativistic stability of matter and show how computer-assisted proofs in interval arithmetic enter. Okay. All right, so let me restate the theorem. The various constants are extremely important, but I'm just going to denote them all in this talk by constant or C0 or C1 or something. Let's just get the ideas. And some of the formulas are going to look complicated. And I urge you that if a formula looks complicated, you should just not pay attention to it. Let's just understand the philosophy. All right, so here's our Hamiltonian with square roots of the Laplacian. Here's our wave function. It is antisymmetric. The y's are simply fixed points in space, the nuclei. I'm going to change notation. The number of electrons is now s instead of n, because I want to use n for something else in just a minute. well, in a few minutes. Okay, so there are s electrons. And the theorem is that this Hamiltonian is greater than or equal to 0 for a particular C0 that we won't worry about today. Okay, now I'd like to give you a crude outline of most of the proof. And it will leave out, it will, I mean, it will contain tremendous gaps, and we will fill in the gaps later. So the first idea of the proof is that there are going to be trick identities, both for the potential energy and for the kinetic energy. And as a result of these trick identities, we're going to be able to write the energy of the system as an integral over all balls. B of ZR is a ball in R3 with center Z and radius R. And we're going to associate in some way an energy to that ball. And we're going to integrate over all balls with respect to this measure. Okay. Notice that if Z is in R3 and R is a radius, dz dr is naturally meters cubed times meters. The meters to the fourth, r to the fifth is meters to the fifth. So this thing has the dimension of 1 over meters, which is the correct units for this Hamiltonian. Okay. Now, all right. So to every ball, there will be an energy. Now, this energy will remember somehow that it came from the kinetic energy and the potential energy of a Coulomb system. Now, if there is any ball that contains no nuclei, then there are no negative terms in the Hamiltonian. The only negative terms in the Hamiltonian come from electrons attracting nuclei. And if there are no nuclei, there is no attraction. And so the energy of a ball containing no nuclei is obviously greater than or equal to 0. And so in this formula, we're immediately going to discard the balls that contain no nuclei. Okay. For the remaining balls, we are going to allocate the energy associated to such a ball, and we're going to simply allocate it equally among the nuclei. So the idea is that we're going to associate an energy to each nucleus, and that energy will come from each ball containing that nucleus, and the share of the total energy that nucleus gets is simply 1 over the number of nuclei. So the energy of each ball is shared equally among the nuclei within that ball. So now, all right, how to put that into formulae? Let's say M of ZR is the number of nuclei in the ball, B of ZR. N of ZR is the number of electrons in the ball, B of ZR. The nuclei are fixed, so M of ZR is simply a number. N of ZR depends on where the electrons are, and the electrons are quantized, so this is actually a function of the x's. Okay, so we have M and N. And so if we allocate energy equally among the nuclei, then we have got the inequality that the total energy of the system, the thing that we want to be positive, is greater than or equal to a sum over the nuclei of, and now what have we got? For each nucleus, this is the share of the energy of the ball allocated to itself, to that nucleus yk. So we divide by the number of nuclei so that we have only that nucleus's fair share of the energy. And then we integrate over all balls with respect to this measure. This is an inequality because I have thrown away the positive energy from balls that contain no nuclei at all. And the plan of showing that this is positive is simply to show that each summand is positive. So for each nucleus, the energy allocated to it is greater than or equal to 0. Okay, so far so good? Okay, so from now on, we're going to fix one particular nucleus. And we're going to make a change of variables. Before, our variables were Z and R. Z is the center of a ball, R is the radius of a ball, but instead of Z, I'm going to use W, where Z and W are related this way. Okay, so that's a simple change of variables. R stays the same, but I change from Z to W. And a point of that is that our ball, B of ZR, contains YK if and only if W is in the unit ball. Okay, and there's a trivial calculation, change of measure. Our measure on the space of balls now looks like this. The r to the fifth is demoted to r squared because somehow this W is dimensionless because the R and Z are both meters. Okay, so if we do that, let's let's introduce some notation. B sub W of R is then B, what I call B of ZR, and M and N are now written like that, with R as the main character and W demoted to a subscript for Z arising in the change of variables. And W is always going to be in the unit ball. Okay. So what we wanted to prove is this. This was our lower bound, except that I'm now rewriting it in terms of the notation of W and R instead of Z and R. This is the guy we want to prove. If we can prove this, we've got the theorem. Okay. Now this is an integral over all W in the unit ball, but what I'm actually going to prove is that the integral over R is greater than or equal to 0 for each fixed W. So life is slowly getting simpler. We have a one parameter family of balls for fixed W. In a moment, I'm going to be speaking about well, now notice when as R approaches 0, our ball shrinks to the particular nucleus YK. So all of these balls contain the fixed nucleus YK. But I'm going to talk about the nearest neighbor to YK, and that depends on W. I don't mean the closest in the ordinary Euclidean metric. What I mean is that starting at R equals 0, I let my ball BW of R expand until, in addition to YK, it contains one other nucleus, and that other nucleus is the nearest neighbor. Conceivably, there's more than one nearest neighbor, I don't care. Okay, so, all right. Similarly for electrons, I can talk about the closest electron or the second closest electron, and that's with respect to this family of balls, BW of R. Okay, now what we're going to do is we're going to take this inequality, this is what we've got to prove, and we're going to reduce it to an inequality for functions of one variable. Furthermore, we're going to take that, that inequality for functions of one variable, and we're going to reduce it to an assertion about solutions of ODE depending on two parameters. And we are then going to take that assertion about ODEs depending on two parameters, and we're going to give a computer-assisted proof of that. Again, I mean, I am a consumer of the computer-assisted proof. Okay, so that's the plan. Okay, now let me backtrack and fill in some of the major gaps. So I said that there are trick identities that allow us to reduce to write the potential and the kinetic energies as integrals over all balls. What are those trick identities? Let me backtrack and introduce those. So I'm going to start with the potential energy. If I have two electrons, let's say one at position X and one at position X prime, here's the Coulomb interaction, and I'm going to write it like that. Notice that for a fixed ball, this is an indicator function. In other words, I have a potential, a two particle potential, which is the simplest thing in the world for a given ball. If both my particles are in the ball, the potential is 1, and otherwise the potential is 0. That's much, much simpler than 1 over the distance, okay? And so if we just sum this elementary identity, which one can easily check, if you sum this over all the pairs of particles, here's what you get for the Coulomb potential. So the full Coulomb potential, which has all of these many terms in it, is an integral over balls of a potential energy associated to the ball, namely the number of pairs of electrons in the ball, the number of pairs of protons in the ball, and the number of electron-proton pairs. So n is the number of electrons in the ball, m is the number of protons in the ball, and if you just sum that previous elementary inequality over all pairs of particles, this is what you get. Notice that already this guy, although it contains mn terms, or of the order of mn terms, think of m and n as being the same order of magnitude, notice that this guy is obviously bounded below by something linear in the number of particles. So that's hopeful. Okay, that's a hopeful sign. Okay, let's do the analogous trick identity for the kinetic energy. So the square root of the Laplacian applied to phi, inner product phi, is given by some important constant that I don't remember, multiplied by the following integral over all balls. So this expression is the kinetic energy associated with one ball. Namely, we integrate, we take the function, we subtract its mean over that ball, and we integrate the square. And so except for the fact that maybe I should be dividing by the volume of the ball, this is sort of the standard deviation or the variance, sorry, of phi. Okay, how much does phi differ from its average? And this is certainly a much simpler thing than the square root of the Laplacian. And if we sum this over all the electrons, we get that the total kinetic energy is equal to an important constant times the kinetic energy associated to a given ball. And here's the formula. And again, I think these formulas look sufficiently complicated that you shouldn't look at them, but they are there. Okay, but they are simply the multi-electron versions of the simple one electron formula. Okay, so now we've succeeded in writing both the kinetic and potential energies as integrals over all balls of something or other. Okay, so I think I filled in the biggest gap in the outline. Okay, now I'd like to explain how to reduce the desired inequality to something involving only one electron. I sincerely hope I remember, oh yes, here. I remembered to recopy what it is we're trying to prove. That's what we're trying to prove. We have fixed the W that tells us how to grow the family of balls, and we fixed the single nuclei YK. Okay, now I'm about to bring in the key hypothesis that the Hamiltonian acts on anti-symmetric wave functions, without which relativistic stability of matter, and for that matter, ordinary stability of matter, are simply false. Okay, so we'd better bring this in. In order to bring this in, I want to recall something from the elementary first course in quantum mechanics. It's the role of antisymmetry. It's called in elementary quantum mechanics the Pauli exclusion principle. So suppose that we have some Hamiltonian, forget about stability of matter, just think of this as maybe the Laplacian in many electrons, and this is a sum over all the electrons of the Laplacian in that single electron, let's say. But we have some multi-particle Hamiltonian, which is a sum of copies of the same Hamiltonian acting on each individual particle. Okay, but now that's acting on psi of s electrons. Okay, imagine you have such a thing. Then you can analyze this guy by separation of variables. So we make for ourselves eigenfunctions and corresponding eigenvalues of the one particle Hamiltonian. Let's list the eigenvalues in increasing order. Okay. And we're going to expand our multi-electron wave functions in terms of the products of these eigenfunctions with coefficients. These are like Fourier coefficients. And so if you apply the Hamiltonian to psi just by elementary separation of variables, the eigenvalue is the sum of these ej1 through ejs, okay? In particular, if our Hamiltonian acts on all L2 wave functions, psi of s electrons, the lowest eigenvalue of this guy is obtained by taking each of these guys to be the lowest eigenvalue of the one electron Hamiltonian, and so it's just s times e1. That's what would happen. That's what would happen if H acted on all psi. But something important is happening because H acts only on antisymmetric psi. And that means that those coefficients, aj1 through ajs, are antisymmetric, at least the non-zero coefficients are antisymmetric. I'm sorry, they're all antisymmetric in these indices. And so the non-zero ones have the j's, have these j's all distinct. One says that no two electrons can be in the same state. They're excluded from being in the same state. And that's the word exclusion in the Pauli exclusion principle. And therefore, the lowest eigenvalue of H acting on antisymmetric wave functions is not simply the number of particles times the lowest eigenvalue, but rather the sum of the first S eigenvalues. Okay. Well, what does that mean for our kinetic energy? All right, so let's take the kinetic energy associated to a ball. Oops, I forgot to multiply this by whatever important dimensionless constant you're supposed to multiply by. Never mind. here is the energy associated to one electron. Can we diagonalize that? Sure. Let's take any orthonormal basis, phi0, phi1, and so on, in which phi0 is a constant. So here's the normalized constant. Okay, this is a constant, and all these others are orthogonal to constants. In that case, if you evaluate this quadratic form, it's 0 on the first guy, on the constant, because guess what? A constant is equal to its average. But all the other eigenvalues are 1, because, and guess what? Anything orthogonal to a constant has average 0. Okay, so the eigenvalues of the one electron kinetic energy are 0, 1, 1, 1, 1, and so on. Okay, that means that if I look at the n electron version for n greater than or equal to 2, the n electron version of the kinetic energy is at least whatever constant I forgot to multiply before times n minus 1, because I'm adding 0, 1, 1, 1, 1 for a total of n things, and I get n minus 1. So I have a trivial lower bound for the kinetic energy that reflects the fact that the wave functions are anti-symmetric. And so I'm going to use this, this lower bound for the kinetic energy if I have any ball that contains at least 2 electrons. But if I have any ball that contains only 1 electron, my lower bound is 0. I don't want to waste the kinetic energy, and so I will just keep it intact. Okay. Now, what I'm going to do is take the lower bound from the kinetic energy. Notice this is simply something determined by the number of electrons. I will regard this as part of the potential energy. I'll move this term from the kinetic energy to the potential energy. So I will not change the total energy, but I will change the kinetic energy by making it smaller, by not including this lower bound. But I will change the potential energy by making it bigger, by including this lower bound when n is greater than or equal to 2. Okay? Okay, no objections. All right. If we do that, and then there's some gymnastics, exchanging sums and integrals, and you have to be a little careful. But if you do that, you discover that the fellow for which we want the lower bound is bounded below by a sum over all the electrons j of integrals like this of the electron attributable, I'm sorry, of the energy associated to electron j. So here I'm not integrating out xj, this hat means omit. And so we're integrating over all the electrons except the jth. The significance of the jth electron is that it's the one that's in the smallest ball, BW. Okay. And so we're integrating and summing, but for each choice of for each choice of j, and then for each choice of all the electrons except electron number j, there is an energy sub j, and we're integrating it. Okay. And what is it? It is a mess to find on the next slide. So there it is. Maybe you shouldn't quite ignore it. Please look. I don't know. Look a little bit. Don't worry, but look. So here we've got a potential energy term, and here we've got a kinetic energy term. This looks familiar. This comes from the kinetic energy. Notice we were dividing by m of r because all the we're sharing this kinetic energy among all the nuclei in the ball, and we're now focusing on a particular nucleus. That's why this appears in the denominator. That comes from the that's one electron. That's one nucleus's share of the repulsion of all the nuclei. This is one nucleus's share of the attraction of the electron to itself, of the single electron to itself. And here, this constant is positive, and it has the right dimensions. It's 1 over a distance. This constant is positive thanks to the fact that we took that n minus 1 and moved it from the kinetic energy to the potential energy. Okay. Okay. And R bar here is the smallest radius in which an electron other than the one we decided was the closest belongs to the ball. And here I have written phi. This is the first, I think the first time maybe the first time I've written phi. Phi is simply psi evaluated where I have fixed all the electrons except the jth, and the jth one is at position x, and that's phi of x. So the significant point of this is that this guy involves only one electron. Okay, all the other electrons are simply fixed. And in order to prove the thing we want and finish proving relativistic stability of matter, I'm going to show that each one of these guys is greater than or equal to 0. Okay, which means the following. We fix a radius r bar, we fix a w in the unit ball, we fix a one electron wave function, we fix an L2 function on the ball of this largest radius, and we look at this quadratic form, and that is supposed to be greater than or equal to 0. And if we can prove that, we can prove the whole shebang. Okay, and we rejoice because this is an inequality for one electron instead of n electrons and m nuclei. Well, once we have finished rejoicing, we then had better prove the theorem. All right, so how are we going to prove this? Well, we've so far, there's still work to do. We've only got one electron, but we still have this increasing integer valued function m of r. We've got a radius r bar, and we've got a w in the unit ball. So our inequality still has a lot of arbitrariness in it. And we're going to simplify the problem by getting rid of most of the stuff it depends on. Okay. First, the easiest thing to get rid of is r bar. The whole problem from beginning to end is dilation invariant. Everything has the dimension of 1 over meters. And so if you can prove the inequality for one value of r bar by making a trivial rescaling, you can prove it for all r bar. And so without loss of generality, we can take r bar equals 1. There is an obvious translation invariance, so we might as well fix our nucleus at the origin. It's obvious that fixing one nucleus changes, if I tell you I'm fixing one particular nucleus, it doesn't really matter that I choose to fix it at the origin. So fine. Okay, those are trivial reductions. Now let's get rid of W. Suppose that I look at two different W's, W and W prime in the unit ball. I have this family of balls and that family of balls. It turns out as an elementary exercise that there is a volume preserving map of R3 to itself that carries that ball to that ball for each R. And as a consequence of that, it doesn't matter what W is. All of these inequalities for all the different W are equivalent. Let's take the simplest W. I'm going to take W equals 0. And so our ball, BW of R, is now simply going to be the ball of radius R centered at the origin. So we've gotten rid of R bar, YK, and W. Okay. Next, we're almost going to get rid of this integer valued function R goes to M of R. And the point is very simple. We want to show that some mess is greater than or equal to 0. And that mess depends on some integer valued function M of R, which takes the values 1, 2, and so on through M max. It's always at least 1 because we fixed a nucleus at the origin, and the origin is in all of these balls. So there's always at least 1 nucleus. Okay, so, well, let's imagine we erase the outermost nucleus. Then we change M of R to the minimum of M of R to this M max minus 1. Okay. What effect does that have on the mess that we're trying to prove is positive? And it turns out to be elementary to check that that decreases the mess provided M max is greater than or equal to 4. Okay. And I promise you that's easy. That's an exercise for a calculus student. So, well, for a calculus student who's getting an A+ in calculus. Okay. So, all right. So that means without loss of generality, we can assume that this M max is less than or equal to 3. And so that means that our M of R is 1 for R from 0 up to some value R1. Then it's 2 starting at R1 up until some value R2. And then it's 3 for R2 for R going from R2 up to 1. Okay. And there are degenerate cases. For example, I could take R2 equal to 1, in which case M would take only the values 1 and 2. Or I could take R2 equal to R1, in which case I jump immediately from 1 to 3. So this includes all the cases. But it means that my M of R, which used to be an arbitrary integer valued function, is now has only 2 degrees of freedom, namely R1 and R2. So there are only 2 free parameters in the problem, R1 and R2, and they are in 0, 1, and R1 is smaller than R2. So we've gotten rid of R bar, W, and in place of this integer valued function, we have just 2 free parameters. So we've reduced the problem to something very, very concrete. Okay, what is the very, very concrete thing to which we are, almost one more reduction than I'll say. Further simplification, phi is a function of on R3, but I can take it to be radial, because if you expand it in spherical harmonics, look at the kinetic energy term. The radial, if phi is radial, subtracting the average does something. But if phi is governed by any spherical harmonic except the radial, the average is automatically 0, and so this is bigger. It means that among all spherical harmonics, the constant spherical harmonic that gives rise to radial functions is worse than any other. And if you can prove our basic inequality for radial functions, it immediately follows for all the other spherical harmonics, and therefore for all functions on R3. So without loss of generality, phi is radial. All right, so, okay, so we have, what we have to prove is that a certain quadratic form acting on functions of one variable is positive definite, and that quadratic form depends on only 2 parameters, R1 and R2, in that relationship in the unit interval, okay? All right, so we've reduced things to a very, very concrete problem. We're getting closer and closer to interval arithmetic. Now, what is that quadratic form? Well, it's this. Here's a kinetic energy term. This constant is important. And here's a potential energy term. And this constant E is given by this formula. Now, M of R, this function M of R, appears in the definition of Q, and it appears in the definition of the constant E. But M of R is not arbitrary. Again, it's this thing that's determined by only 2 parameters and takes the values 1, 2, and 3. So this is a quadratic form depending on only 2 free parameters. Okay, and what? Okay, and because this, well, all right, you can just write this out, and it takes the form of the constant E multiplied by the L2 norm squared plus some particular explicit self-adjoint operator A acting on U like that, and A has the form of a multiplication plus an integral kernel. So it's a simple elementary looking fellow, okay? And here are E and M of R are as before. So we want to prove that this guy is greater than or equal to 0. What that means is that A is greater than or equal to minus E. Now, A and E both depend on these R1 and R2, but in at least one particular case, if you take R1 and R2 to be both equal to 1, there is some elementary inequality using the Mellin transform, which you can use to prove that A is actually strictly greater than minus E. So in this one starting case, this is true, and in fact, it's true with strict inequality. By a continuity argument in which we continuously vary R1 and R2, we can see that this desired inequality will hold as long as we, in fact, with strict inequality, as long as we show that minus E is never in the spectrum of the operator A. Okay. All right, we're getting closer to something computer assisted. So how can we tell whether minus E lies in the spectrum of A? And the answer is that this equation, which obviously the analysis of this equation is going to tell us whether E is in the spectrum of A. If you take this fact and remember the definition of A, if you take this equation and differentiate it twice, you will get an ODE. Maybe you have to differentiate it once and then multiply by something and then differentiate again. But some elementary manipulation produces from this equation an ODE. And therefore, the statement that E does not lie in the spectrum of A comes down to an assertion about solutions of ODEs. Now, I'm afraid that this is getting too vague. So in the next couple of slides, I'm actually going to show you what you have to prove about ODEs. And I'm making the change of variables that what I called R is now E to the T. So R varied from 0 to 1. T is going to vary from minus infinity to 0. Okay. So here are the exact assertions about ODEs. In place of R1 and R2, I now have T1 and T2. So first of all, starting at t equals 0 and solving down to t equals T2, I solve this ordinary differential equation, which doesn't look so bad, with these initial conditions. At 0, f is 0, and its t derivative is 1. All right, so I'm solving an ODE. All right, I propagate that ODE back to t equals T2, and so now I know f of T2, and I know the derivative of f at T2. Okay, next we solve another slightly different looking ODE from T2 down to T1 with the initial conditions that g at T2 is equal to f of T2, which I know, and I have this equation that tells me g of T2 in terms of the derivative of f at T2, which I just calculated. So solving the previous equation gives me the initial conditions for this equation. And I propagate the solutions of this back to t equals T1. Okay, I set that aside and I solve a different problem starting at t equals minus infinity and propagating up to T1. And here's the equation that you have to solve up to t equals T1. And let's see, this is a regular singular point, so it has two solutions. It has one exponentially, one solution that looks like this, and one solution that's much bigger as t tends to minus infinity. And so this plays the role of a boundary condition. Okay, so now we've solved some stuff from 0 down to T1, and we've also solved from minus infinity up to T1. And so we have our functions g and h, which are both defined with at T1, and we say that a match occurs for epsilon, or for T1 and T2, if these two vectors, this is the one that came up from minus infinity, and this is the one that came down from 0. If these two vectors are proportional to each other, then a match occurs. And one can check that minus e is not in the spectrum of our operator A, and therefore the whole theorem that we want to prove is true. It all comes down to proving that a match never occurs. Okay, so we're going to define some discriminant, which is, let's say, the determinant of the matrix that, and that discriminant is supposed to be never equal to 0. Okay, now we must exclude matches. That means we have to consider all T1, T2 down to minus infinity. Of course, computer-assisted proofs don't particularly like minus infinity, and so one reduces things by some elementary tricks to a bounded domain. And I'm going to be a little vague. Well, I'm going to be completely vague about what the tricks are. Let's just, by a polite fiction, pretend here that it's enough to look at a compact region in the space of all T1, T2. And so what I've got to show is that this elementary function, this discriminant, which is defined in terms of solutions of ODEs, is never 0. Okay. Well, that is such an explicit statement that one can hope to apply computer-assisted methods. Let me just set the stage a little bit and then explain from the point of view of the ignorant consumer how the computer-assisted math works. Okay, we're going to take the region of relevant T1, T2, and we're going to cover it by little rectangles. And so there are a lot of these little rectangles in the space of T1, T2. There are a lot of them, but we have a computer, so if there are 1,000 of them, so what? We look individually at each one of them, and we want to exclude matches for T1 and T2 in that interval. How do we do it? Okay, and now comes the idea of interval arithmetic. So suppose that I told you a particular T1 and a particular T2, and so I'm just trying to calculate a particular discriminant by solving some particular elementary ODEs. Okay, well, one could do that using interval arithmetic. How does interval arithmetic proceed? Well, T1 and T2 are perhaps not machine numbers, but they are contained in tiny intervals. And the very nature of interval arithmetic is that it doesn't just deal with particular T1 and T2, but rather it establishes something or other for all T1 in the interval I nu 1 prime, the little interval in which it lives, and for all T2 in the interval in which it lives, okay? And so using interval arithmetic, one makes a calculation of this discriminant, and if you're really unlucky, that interval will contain 0 and you won't know whether the discriminant is 0 or not. But if you are lucky and that interval does not contain 0, you have excluded the match for particular T1 and T2. So the point is that you do not look merely at individual T1 and T2, but by the very nature of interval arithmetic, you are looking at intervals in the space of all T1 and intervals in the space of all T2. You are already looking at rectangles. However, at least at the time, I don't claim to be anywhere near current, but at least at the time, this was a radical departure from the standard philosophy of interval arithmetic, because we have to deal with fat intervals. Normally in interval arithmetic, you're doing a calculation and you want to take your intervals as small as possible to minimize round-off error, and because round-off errors propagate, you'd better take small intervals to start with. Here we have to take a fat interval because we want to cover our region of relevant T1, T2 by, I mean, it's fine to cover it by 1,000 rectangles, but it's not fine to cover it by 10 to the 48 rectangles. So, so we have to do interval arithmetic with fat intervals. And so the plan is going to be that we take a T1 interval and a T2 interval, and they are fat intervals, and we're going to compute ODE solutions using interval arithmetic, taking that and that as our values of T1 in interval arithmetic. And as a result of doing an ODE calculation in interval arithmetic, we will obtain an interval that I'm going to call script I of I1 and I2, which is guaranteed to contain the discriminant we want whenever T1 is in its interval and whenever T2 is in its interval. And so we will, well, perhaps the whole computation will fail, but if it doesn't abort and if it computes an interval, we can then look at that interval and see whether it contains 0. If it does not contain 0, we have succeeded in excluding the Cartesian product of I1 with I2. But on the other hand, if it does contain 0, then we have failed. What to do if we have failed? Well, if we have failed, all right, we don't yet know that this discriminant is non-zero. What do we do? And the answer is we subdivide. And so here was an interval I1 cross I2 in the space of all T1, T2, and we tried interval arithmetic and it didn't work. Well, never mind, let's divide into this rectangle, this, and this. These are smaller, and so our interval arithmetic has a better chance to succeed. And so if it ever happens that we do a calculation here and we fail, we don't just give up, but we subdivide and try again. And if these guys succeed, that's great. But let's say this guy fails, we won't just quit, we will subdivide it. This is actually the Calderon-Zygmunt decomposition from classical Fourier analysis, which I learned as a kid and which I keep discovering has limitless uses. And so we're recursively going to call subroutines that tried to rule out the discriminant being 0 in a rectangle. Of course, we could get unlucky and just keep cutting and cutting and cutting and failing and failing. And if our rectangles just get too small, then we quit. But in fact, all right, so our program will either report failure because we just chop so finely that we give up, or it will report success, namely matches, namely discriminant 0 are excluded. If that has any chance at all, we had better have an ultra-stable ODE solver in which fat intervals do not propagate big errors. And Rafa took advantage of the particular simple form of our ODEs to make power series solutions with controlled errors, and he actually succeeded in producing such an ultra-stable ODE solver for these ODEs that the whole thing works. So it works, and to this day, I am amazed that it was possible, but indeed Rafa was able to do it, and that's it. So that proves the theorem, and that's how I first became a consumer of computer-assisted math. And okay, I've skipped over a lot of stuff. I don't think anybody particularly is desperate to read the paper and get all the details, but here's the reference in case, for completeness. The details can be found in there. And thank you for listening. That's it. Thanks.
Yes, thank you very much for this wonderful talk. Are there any questions maybe from the audience?
May I ask on the original model which you used? You see, when you come from the relativistic kinetic energy, then shouldn't we then take minus Laplacian plus m squared and then take the root and then minus m?
Oh, yes. So yes, if you do that, so let's see, that is greater than or equal to the square root of minus the Laplacian minus a constant.
Yes.
Okay. And so what one would get is that version of the kinetic energy is greater than or equal. I'm sorry, that version of the Hamiltonian with what you said is then greater than or equal to minus some constant times the number of particles, rather than being greater than or equal to 0.
What you want to say that if we change the model in that direction, which I was suggesting, then we don't get a difference in the result concerning stability of matter.
Yes, thank you. That's what I should have said. Yes, yes.
All right. Okay.
The big difference, both physically and mathematically, is whether the thing is bounded below or not.
Yeah, of course.
So,
yeah.
Right. So for example, let's say for a neutron star, the idea was that you have, on the one hand, you have, let's say, gravity. So you put in Coulomb forces, but they're all attractive, no repulsion at all. Mm-hmm. And then on the other hand, you have this square root of the Laplacian times some constant. And because of the Pauli exclusion principle, that in effect is repulsion.
Yes, right.
Okay, and then you see how big does the attraction win or does the repulsion win? And you assume that everything is rotationally symmetric and may just do the simplest thing. And you find that if that there is some order of magnitude, it's only an order of magnitude because this isn't correct relativistic quantum mechanics. But there is some size of the star, and if the star is bigger than that, gravitational attraction wins over the Pauli exclusion principle, and the star collapses. And so that was I believe that was the origin of the first prediction of the formation of a neutron star. Okay, and the analogous thing in atomic physics, again, it's not correct relativistic physics, but maybe it predicts orders of magnitude. It would say that, let's say, an atom collapses if it is too big, and so in fact, if you do the calculation, I think this model would say that something around uranium cannot exist; it collapses. And well, uranium exists, and okay, but nothing 50% bigger than uranium exists. And I believe the explanation is this.
Okay, thank you.
Oh, actually, wait. Also, oh God, my physics is so pathetic. Not only are electrons sick, but also nuclei are sick when they get too big. So maybe the huge, maybe the instability of the nucleus takes over before the collapse of the atom. And anyway, there's nothing 50% bigger than uranium.
And all that is not is neither captured by this minus Laplacian to the power 1/2 model, nor by the model minus Laplacian plus m squared 1 to the 1/2 minus m.
So both right, but so both models predict collapse at the same. I mean, whether something collapses or not is independent of which version you use it. Use presumably my square root of the Laplacian is more inaccurate than your square root of Laplacian plus mass squared, square root minus mass. I mean, they're both inaccurate. Yours is less inaccurate, but mathematically, for purposes of deciding whether something collapses,
that's the same.
doesn't matter.
Yeah, okay.
Okay, and that applies also to atoms. So if you pretend that nuclei were just points, so they're automatically stable, then the physical prediction of this is that because of the electrons, because of the attraction of the electrons to the nucleus, that I mean the electrons will collapse into the nucleus if the atom gets too big.
Other questions?
Oh, actually, I have a question. So back in, oh, I'm sorry. I should
go
answer
ahead. Go ahead.
Okay.
Yeah.
Back in the day, this was a radical use of computer-assisted math, because instead of proving that some equation is true or solving some equation using the contraction mapping theorem or something, instead of that, one is using computer-assisted methods to prove that something doesn't happen. Okay. How would one do that nowadays? I imagine, correct me if I'm wrong, I imagine that is a very standard thing to do now. And if so, I wonder how do people do it now?
I think computer-assisted proof means proof inequalities, right? That's what you can do by computer-assisted proof.
Yes.
And when you do something by contraction mapping theorem, then you prove the assumptions of the contraction mapping theorem by proving inequalities.
Sure.
And proving inequalities is, of course, also proving that something does not hold, as in your case. You also prove inequality.
Right.
Inequality where the sign doesn't matter, just not equal.
Right.
And so that's actually, that is within the philosophy of a computer-assisted proof. You prove inequality.
Oh, okay.
You can never prove equalities directly.
That I understand, but again, as a practical matter, right? You have to use something fat, right? I mean, in principle, you could take a whole lot of, well, suppose that some function of one variable is not zero. You could take a whole lot of little tiny intervals and prove by interval arithmetic that it that the thing you compute is never zero. And certainly I understand your point. But in order for the program to terminate in our lifetime, one has to do something more. And I wonder what do people do in practice? Am I right? Such problems occur all the time, right? You want to prove inequalities.
I mean, what you did is sort of the idea for a lot of these kind of things, right? You try on a big box, and when you fail, you make a smaller box.
I see.
I'm reminded of Jonathan Jacquet's thesis, where he recently settled Wright's and Jones conjecture for Wright's equation, and he had to rule out lots of solutions of delay differential equations. And did something very much like you did, a branch and bound kind of. I mean, Jonathan's here. Maybe he wants to say something.
Yeah. So in my thesis, I was interested in proving that a unique solution to a delay differential equation exists, a periodic solution.
Okay.
And so, I mean, one part is like doing a curve and showing that along the curve there's no folds and whatnot. But then the problem, as you said, is away from this one branch of periodic solutions, how do you rule out solutions? So what I did is I converted it into an infinite sequence of Fourier coefficients and equations that need to be satisfied. And then the question is, how do I rule out zeros of this infinite dimensional function? And so, as you did, you try and show in this fat box that f of x does not equal 0. And if it doesn't work, then you subdivide and so forth.
I see.
But I think I mean, if you just throw the computer at it, it's gonna explode. So you need to be a bit smart about it. And so asking sort of orthogonal questions. So like suppose you also know that some energy estimate needs to be satisfied. And so instead of just looking at the one's equation is satisfied, you also say, okay, well, I know that solutions can't be too big and solutions can't be too small. And yeah.
I see. So then maybe you have different reasons to rule out rectangles.
I think the divide and conquer, I think we should now call it Calderon-Zygmunt decomposition from now on, that's clear. So that is quite, that is very popular, but of course, if you are in higher dimensions, that quickly becomes difficult. So that is where you are gonna need, as Jonathan just said, more clever things to start doing things. Yeah.
Jonathan, you were in infinite dimensions?
Yes.
Oh dear, what do you do about that?
Well, so again, you want a compact subspace. So if you have a compact set of solutions where you're looking for a solution, you can cover it by finite ways.
Yeah, and in this case, compactness comes from regularity of periodic solutions, because periodic solutions, they have Fourier coefficients which decay very fast, and that regularity is used to kind of compactify the space of Fourier coefficients.
I see, interesting.
But of course, then in the compact case, then the sets are no longer fat in some sense, right? Compact sets are always non-fat.
Yeah.
So then you escape the problem by non-fat sets, so to say.
Well, they're still fat in finite dimensions, right? It's just that the infinite tail basically is not fat anymore.
Okay, so
infinite dimensions, they are not fat. That's what I mean.
Right.
Okay, I'm reminded of the movie The Devil Wears Prada. What is the definition of fat? Anyway. Okay, that stopped the conversation.
Are there any other questions? I have maybe a question about motivation. Were you always looking to reduce it to something that could be done by computer, or were you reducing beautiful reductions? And then finally, in the end, you couldn't reduce any further. And you had to involve a computer.
There's a cute story. So this was the early 80s, and in our household was a wonderful new toy, an Apple II Plus. Okay. And so what could I do with the Apple II Plus? Well, one of the things I could do is solve ODEs. On the other hand, I was very interested in quantum mechanics. I had spent years in fruitful conversation with Barry Simon before he moved from Princeton to Caltech. And he got me interested in things like what I spoke about today. And so I reduced and discovered, oh, hey, this is a statement about ODE. Oh boy, I can run it on the computer. And so I spent hours running ODEs on the computer. And of course, this is a function of two variables, and you can graph it for, you can compute it for lots and lots of particular values, not rigorously, but I think convincingly. And oh boy, this function is never zero. Oh boy, well, okay, how can I prove it? And so I was teaching. I'm teaching a graduate class in this, and fortunately, Rafa was sitting in, and he said, "You know what? I know what we're going to do. We're going to do computer-assisted math." Computer-assisted math? Well, I'd heard of it because I'd gone to lectures on Lanford's work on on renormalization. Oh, computer assisted. Oh, fantastic. And Rafa went to work, and I sat back and watched, and lo and behold. So that's what happened.
Excellent. Yeah, very nice. Are there any other questions?
If I may ask another question, you used, I'm not quite sure about your general assumptions about the Hamiltonian. So you used the smallest eigenvalue, and you used the sum of the first S smallest eigenvalues to get a lower bound. But what happens if the operator has essential spectrum? So
okay. That then I mean, once you hit the essential spectrum, you are out of luck. The only, I mean, this is all very specific to one particular Hamiltonian, and it happened that not entirely by coincidence, by design, the kinetic energy associated to one electron is a very, very, very simple thing. Okay. That was the point of this integration over balls. That whereas the object that you're originally trying to deal with, this relativistic or pseudo-relativistic Hamiltonian, is a complicated object. Nevertheless, you can write it as an integral over balls of things that look much simpler, and they're still not trivial, but they look much simpler. And in particular, the kinetic energy Hamiltonian that you have to deal with for a particular ball just has the eigenvalues 0, 1, 1, 1, 1, 1. But if there is essential spectrum, I guess as soon as you hit the bottom of the essential spectrum,
so you do everything below the essential spectrum, so to say. You have to take Hamiltonians which start with an initial discrete spectrum. Is that right?
Well, again, I am looking at one particular Hamiltonian, which unfortunately depends on a whole lot of stuff. You know, how many electrons, how many nuclei, where are the nuclei? But if you tell me that there are 10 to the 28th nuclei, and here they are, okay, and there are 10 to the 28th electrons, that specifies the Hamiltonian. Okay.
But you could not do that, for example, if you have no nuclei, if you have a free electron or free electrons or something like that.
If you have free electrons. Wait, I see. Jean-Philippe has to pick up his daughter. Please pick up your daughter, please. Of course, anyone who has to leave should leave, of course.
It was a beautiful talk. Thank you very much. Bye-bye.
Okay, so yeah, if there are free electrons, no nuclei, then remember at the beginning I discarded all the balls at the very beginning. I wrote I discarded all the balls that contain no nuclei, and so I would have discarded all balls, and so I would be left with the operator 0. And my task would be to prove that that's greater than or equal to 0. Okay, I can do that. Okay.
Without the computer. Yeah.
Without the computer.
Any other questions? Well, if not, then I propose we thank our speaker one more time. And
thank you for listening.
Thank you very, very much. And to the audience, thank you for being here, and hope to see many of you again next week when we have a talk by Vladimir Svirak. Thank you, and bye-bye.
Bye-bye.
And thank you very much for the wonderful talk. I think
thanks.
I saw a lot of people enjoying it, so that's great.